Okay, so we previously looked at finding a general solution to Laplace's equation in spherical coordinates. Now we're going to do the same thing here except for cylindrical coordinates. And we're going to look at only the case where the potential depends on S. So Laplace's equation in cylindrical coordinates is given as above. Okay, so that can be obtained in your Griffiths textbook or from other relevant sources. And since it depends, the potential depends on S only, what we can write is the phi derivatives equal to the z derivative, and these are going to be equal to 0. Okay, so the Laplace equation is just going to depend on that term. So if we just write this out, so we have the Laplace equation will equal to 1 over s derivative with respect to s of s dv ds. Okay, so the solution of v for the second order potential equation must satisfy the following first order potential equation, where we have s dv of ds is going to be equal to some constant which we're going to call a. Okay, so now what we can do is we can of course bring that over, and this can now be written as it's going to be equal to a divided by s. Okay, so this is our first order differential equation. We've written as a divided by s, and the general solution to this first order differential equation is going to be v of s will be equal to our constant a by natural log of s plus some constant b. Okay, so what this gives us is the general solution to Laplace equation in cylindrical coordinates where the potential depends only on s. Now, a and b are constants, and we can determine those by the appropriate boundary conditions. One point to note is that we cannot set our reference point to be at infinity or even at 0, because what will happen is the potential will go to infinity. So what we need to do is we need to set some other boundary conditions, and this is what we're going to tackle in the next couple of lessons. So some important points to take note of now to do with boundary conditions and uniqueness theorems is that for the first uniqueness theorem, if you obtain a solution that satisfies both Poisson's equation and it also satisfies it for a given set of boundary conditions, then that is your solution. There can be no other solution, okay? So there is only ever one solution to Poisson's equation for a given set of boundary conditions. The second theorem has to do with some volume which contains some specified charge density, which is given by rho, and it's surrounded by a number of conductors which are given, for example, Q1 and Q2 and so forth. And the second uniqueness theorem states that the electric field can be determined if we know what the total charge on each of these conductors are that surrounds this region, and also the charge distribution in the region between the conductors must be known. So these are two conditions that we're going to come across as we move through the next couple of lectures.